Hmm. Okay, guys, welcome back yet again. Today we're on to 4.4, which is about tangent lines, tangent lines, and linear approximations. So by now, you hopefully have a sense that we are, broadly speaking, we're extending all of the basic ideas of one variable calculus to the setting of multiple variables. And one of the number one things that you do in one variable calculus, once you understand the basic ideas, is you use calculus to approximate, difficult functions. So they say that in the following way. Let's say you know very little about this black function, but you call it f, and maybe you are interested in the value of f at some point, and let's say that point is right here. So maybe you get to that point by adding a delta x, a little bit of x to some starting point A, and the tangent line to f takes some value there. And that value is not f of A plus delta x. We'll put it over here though, but it's close. And I'll put in parentheses here. This is not really what we're getting into right now, but if you know what a Taylor series is, you can get really close, right? You can get very, very, very close without ever actually knowing what the value of the function is. So in particular, differentiable calculus or differential calculus is a technique or whatever, a family of techniques, or let me say it gives rise to a family of techniques for making approximations, which is huge in particular if you're doing things like numerical analysis or you're using your calculator ever to figure out like the sign of something and so on. Using computers to approximate things relies heavily on ideas like Taylor series and tangent lines. So if you feel like that ever made sense to you before, then maybe you feel motivated that we want to develop those same ideas for multiple variables, and we get to one immediate issue, which I've already mentioned. Whoops, sorry, which is that we're going to stick to 2D for right now. Uh, in 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 2D, the analogous concept. So the analogous concept is a what? 5, 4, 3, 2, 1 tangent plane. Right. So we saw this. I sketched this, I think, at one point. The analogous concept is a. So we've got to build this up. A quick sketch to motivate the words I'm about to write. Let's try to make things interesting by not continuing with the sphere. Let's go with an upward facing paraboloid. So we'll go up like this and up like this, and the same thing in the other two directions. I kind of wish that that touched. Okay, so this could, for instance, be z equals x squared plus y squared. If you pick a point on the graph of this function, you should believe, if you very confidently, at least at this point, that there are many tangent lines. There's a two-dimensional space determined by these tangent lines. And that space is a plane, and it's got a name. You can take a guess. Uh, the tangent plane, the tangent plane. Come on, like tangent plane at some starting point. So I guess I'll say at x comma y, where x comma y is the point that we're starting at. So this is some point in the xy plane. Maybe it's right here, right? That's like the point we plugged in. So if that point is x comma y, then the tangent plane at x comma y is this green plane that I'm drawing here. Okay, pictures are great, but they're not definitions. So we'll go with the definition. Um, the tangent plane, so this is what we're defining, at x comma y, the tangent plane of a function f is the set of all tangent lines. Let's just say to the graph of f at this point, x comma y. Okay, this is the first part of what today is about. We're going to have to do a recall. There's all kinds of stuff you're expected to know to even start this course. And the mathematics for expressing planes and lines and so on is definitely one of the prerequisites. Sorry, I'm trying to find a place to put my coffee. Okay, so I'm going to try to do this real quick because it's good to see things again. But technically, you should already know everything I'm about to say right now. Whoops. So there's like a TLDR that I could say, right? So AX plus BY plus CZ equals D. That's a plane right there. That's how you can express a plane. Another way of doing a plane is the second one. This is one I care about, is going to be Z equals, and I'm going to do it like this. AX minus X initial plus B, BY minus Y initial. B minus Y initial. So this is also a formula that gives rise to a plane. I want to talk about this. Oh, no, sorry, and plus, put a plus C in there. So that is the meat of what I'm about to talk about, but let's go through it slowly. Let's say that I wanted to make a flat plane. Whoops, a horizontal plane. I can do so by starting at a point. Maybe let's keep it interesting. Maybe we'll use 2. And I want it to not change in the X direction because I want it to be horizontal. And I want it to not change, whoops, not change in the Y direction because I want it to be horizontal. By now, after the last lecture, you know that these are slopes here, right? This is the derivative in the X direction of the function, and the second line I drew is the derivative in the Y direction. But in the context of expressing a plane, we can do this in the following way. We state Z, it started at 2, and we're going to add nothing. That's 0 times however much we go in the X direction. And we're going to add nothing for however much we go in the Y direction. That's the same as just saying Z equals 2. Z equals the constant 2 is a plane. It's a plane that has 0 slope in every direction. It's a flat horizontal plane. Let's do one more example real quick. What if I wanted to start at the same point Let's call that 2 there. But I wanted it to go up in the x direction. So let's just encode that part. Z equals, well, we're starting at 2, but we're going to go up. Let's give it a slope of 1. We'll go up by 1 times x. And then let's just not go up at all in the y direction. So it stays flat in the y direction. We, again, generate a plane. Hopefully you can kind of see it, though. It's tilted upward now. And then a couple more examples. I could do like example, let's do like z equals 2 plus 2x minus y. Z equals -1 minus 3x plus 5y. Right, we're specifying some starting points, and then the 2 or the -1, the -3, and the 5. This is saying how much to go up or down in various directions. One more level of complexity. I don't have to start at the origin. I could go ahead and uh, X, Y, Z, pick some other point. X initial, Y initial. Say like right there. And I could say, well, at that point, the function Z equals, maybe 5. Maybe that's 5 right there. So I want to start off at Z equals 5, but I want to go down in the X direction. Let's say at a slope of 1. So I want to go down, and it's not X that I put here. Now it's X minus X initial. How far away from that starting X coordinate we go. And then let's go, keep it interesting. We'll go up in the Y direction. So up in this direction like so. And so we would go up, let's say at a slope of 1, for however far we deviate from the starting Y coordinate. And then again, this gives rise to a plane. But we've kind of conceived of the plane by this starting point that's not coming from the origin, but it's coming from starting over X initial, Y initial. Same idea. So if you understand all of that, then you can see why this is a general formula for a plane other than planes with infinite slope, right? X initial and Y initial is your starting point. A and B are the slopes, and then C is the height at that starting point. Once you know A, B, and C, you can always express the plane by appealing to this formula. So that's all an aside. That's all stuff you're already supposed to know. And with everything that I've said so far, now we jump into our first example. So let's go ahead and throw a function on the screen. Give me 1 second to find my first example. Yeah, okay, so they just give us this function here. I'm sorry, these functions all take so long to write, but it is what it is. 2x squared minus 3xy plus 8y squared, 8y squared, plus 2x minus 4y plus 2x minus 4y plus 4. And they give us a starting point. I'll write it right here. X initial, Y initial is 2 comma -1. I don't want to write these words out, but what it says is, find the tangent plane to the graph of f at the point X initial, Y initial. So we're just going to do everything I just said for this point and this function. All right, let's go right ahead and get to that. So first insight. If I'm writing out, so let's do this as an idea. We'll do this in a different color. Idea. Well, I'm looking for a plane. What's a plane? Z equals. I need a starting value. What should my starting value be? Take a second and think about it. You got it. It's got to be the value of the function at the point 2 comma 1. So let's start with that. I'm gonna just do it in my head because I don't want to write out the arithmetic. 2 squared is 4, that's 8. 8 plus 6 is, well, okay, 14. Plus 8 is 22. Plus 4 and plus 4 plus 4 plus 4 is plus 12 is 34. Let's see, we got that right there. 2 times 2 is 4, negative plus 4 and 4, that's definitely 12. 8 is 20. 26. 26 plus 2 times 2 times 2 is 8 is 30. Yeah, I believe it. Yep. Okay, 34. So let's go ahead and put that in. Well, let me start. Well, okay, yeah, 34. Uh, I actually, you know what? Actually, hold on a second. That's really going to be what we're going to write in black. So let me get that. We're going to write that z equals 34 plus. But that's not really the idea. The idea is we want to know what the value of the function is at that starting point, which is 34. Mm. And then what? Well, I don't necessarily want a flat plane, right? If you go back up to, do I have a good picture for this? I guess kind of the green one. The plane won't be flat, but it will have slopes, some slopes anyways, that we can figure out right now. How much should it go up or down in the X direction? Take a moment, try to decide. Yes, it should go up by, so don't forget, I've got this other notation, this subscript notation, F sub X. So this notation says the derivative in the X direction, the first derivative, uh, and then we've got to go at the point we care about. That's the slope, X minus X initial, in the X direction. So I'm starting off at the function value. And then I'm going to go up in the X direction this much, or at this rate. And then, of course, hopefully it's clear, we're also going to have a slope in the Y direction. And it's got to be the derivative in the Y direction. So that's the idea. So 34 plus something and something. And how are we going to find those somethings? Um, Follow the information we've been taught to look for. What is the first derivative of this function with respect to X? Starting over here, I bring down that 2, I get 8x minus 3y plus 0 plus 2 minus 0 equals 8x minus 3y plus 2. There's also a derivative in the y direction, and that one is 0 minus 3x plus 16y plus 0 minus 4 plus 0. Minus 3x plus 16y minus 4. Yeah. Okay, that's kind of an aside, right? We it's nice that we found those derivatives, but that's not really what we want. We've been given a specific point, and at that point, there are some specific slopes. So this is going to come about by plugging into -1 into these functions. If you plug in 2, -1 to the first function, you will get 8 plus 3 is 11 plus 2 is 13. 8? No. That's 16. Sorry. 8 times 2 is 16 plus 3 is 19 plus 2 is 21. And one more time. 16 plus 3 is 19 plus 2 is 21. And then I also want to know what the derivative is in the y direction when I plug in these points. And then this is negative 6 minus 16 is negative 22. It's negative 26. Negative 6, negative 16 is negative 22 minus 4 is, yep, negative 26. I believe it. And that's really all the hard parts, right? Now we can complete this idea here. We start off at 34. We go up at a rate of 21 in the X direction. We gotta remember, don't forget we start at 2. X starts at 2. And we want to go down at a rate of 26 in the Y direction, I'm going to just put +1. Whoops. We're done. Nice, easy first example. If you understand that a tangent plane, right, which by definition contains all the tangent lines, must contain the tangent line in the y direction and the tangent line in the x direction, first idea, and you understand how to express planes using these formulas, then that right there has got to be the tangent plane, an equation for the tangent plane to this function at this point, because it starts at that point and it's been designed to contain the tangent line in the x direction and the tangent line in the y direction, and that's it. We're done. Okay, that's my first example. As always, if we were in person, I would pause here and ask if anybody had any questions. I'm going to go through one more example using trig functions just for completeness, and then we'll get into some other stuff. So one more example, it's going to be the exact same kind of problem. Here's what they give us. Whoops, hold on a second. Sine 2x cosine 3y, sine 2x cosine 3y, and they give us a starting point. I'll say x initial, y initial. Pi over 3, pi over 4. Pi over 3, pi over 4. Okay, so we're doing all the exact same stuff again. I need to know what this function equals at this point, so I know where to start my plane. Pi over 3, I don't want to do trig functions in my head. 2 times pi over 3 is 2 pi over 3. Here's 1 pi over 3. Here's 2 pi over 3. The sine of that is a positive number. It's the bigger one, so it's root 3 over 2. Root 3 over 2. Oops. Root 3 over 2. Uh, and then I need cosine of 3 pi over 4. Same deal. So pi over 4, 2 pi over 4, 3 pi over 4. Cosine is negative over there. So this is sine of 2x, and then cosine of 3 pi over 4. This is 2 over root 2 root 2 over 2. Excuse me, root 2 over 2. Okay, sine of 2 pi over 3, cosine of 3 pi over 4. I believe it. This should have a negative sign on it. Equals negative root 6 over 4. That's over the starting point, pi over 3, pi over 4. That's what the function equals. So that's where we will start our plane, but we're going to need some slopes. I'm going to need a slope in the x direction, and I'm going to need a slope in the y direction. Let's go ahead and find these real quick. If you differentiate this guy up here with respect to x, you will get 2 cosine 2x cosine 3y. Whoops. If you differentiate it with respect to y, you will get 3 negative sine 2x sine 3y. I've got to evaluate these functions at the point I was given, so I can know what the slopes are at that exact point, not elsewhere. If you plug in pi over 3 up here, you're going to get, now it's cosine of 2 pi over 3. That's the smaller one. So that's 1/2. And then I want the same cosine. So that's still negative root 2 over 2. This just comes out to be negative root 2 over 2 because the 2 and the 1/2 cancel. And then if you do the derivative in the y direction, -3, I want the sine of 2 pi over 3. But now I want the sine of 3 pi over 4. That's positive. And that's also root 2 over 2 in magnitude. So that now is a little more complicated looking. -3 root 6 over 4. Get that right? -3 root 6 over 4. That looks good to me. Okay. So again, we're looking for a tangent plane. So we have a starting value, z equals -√6 over 4. But we need to have a slope in the x direction, which in this case is -√2 over 2. This slope is measures how much we go up or down as we deviate from the point pi over 3, or from the coordinate pi over 3 in x. And then we've also got a negative slope in the other direction, -3 root 6 over 4. And this is measured in how far y deviates from pi over 4. Pi over 4. Okay, we did it again. So that's two examples where we are finding an equation for a tangent plane based using first derivatives. What's next? Yeah. So let me go back to my first picture to re-stimulate something. You probably remember having to do problems that said something like, use a linear approximation to the function f to evaluate, f of some weird point. Use a linear approximation to evaluate. Use a linear approximation to evaluate. So we're going to want to do that here in 2D as well. Let me see if I can do one more quick sketch. I'm going to go back to the sphere because I've only got so many drawings. So I got to keep on kind of using the ones that I know how to do. This is a picture for linear approximations. Approx. Let's zoom in a second. Can I do something more interesting in a sphere? Well, we can make it, yeah, we can do it a little bit different just for creativity's sake. Let's make it elliptical and we'll make it kind of tall and thin. So let's make its height like way up here. So this is maybe like a downward facing elliptic paraboloid. Yeah. Okay. Let's imagine that we were looking at a function like this. And we had some starting point. So let's say our starting point is, where's going to be the easiest way to draw this? Maybe like right here. So that's in the plane. That takes a value on the surface of the function. This gives rise to a tangent plane. And now let's zoom in here and just think about this. And let's say we wanted to evaluate the blue function at a nearby point. Maybe the nearby point is right here. Let's go right here. Well, the value of the blue function at that gold point is, maybe somewhere like right there, lying on the blue curve. But then if you're following along my picture, then you can imagine that just above that somewhere is the value of the plane. The value of the plane takes over that point. And that value there is our approximation. Approximation. So if you understand this idea, then hopefully the example I'm about to do will make sense. But we're going to quote unquote use a linear approximation, so that's a tangent plane, to approximate a function. Let's go ahead and do that. Ba-dum, bum, bum. We'll go with this guy right here. And actually, you know what? I surprise myself sometimes. This is a downward facing ellipse. Oh, no, this is a cone. Never mind, this is a little different. Okay, f of x. So this is what they give us. Root 41 minus 4x squared. Wow, I did that twice today. 41 minus 4x squared minus y squared. So that's a function. And they give us, this is what they ask us to do. Approximate the value of this function at this point, 2.1, 2.9. And then I'm going to just put this using 2, 3. And so we're going to find the tangent plane at 2, 3. Find an equation for the tangent plane. And once we have that equation, we're just going to plug in 2.1, 2.9. And that's going to be like an approximation to this function here. So one more time, I'm going to do everything that I've already done today. I need to know what f is at 2, 3. 4 times 4 is 16. 16 and 9 is 25. Uh, 25. Sorry. Hold on a second. Hold on. Crap. Relax. So nothing is burning. I think my fire alarms are broken because they do that sometimes. Um, ba 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 bum. Yeah, 16 and 9 is 25, and then so 16 more to 41. So this is root 16 is 4. Okay, that's where our plane is going to start. But we're also going to need derivatives in each of the primary directions. If you differentiate with respect, okay, so there's an issue here. Sorry, this is a kind of an uh, in-depth derivative. You've got to apply the chain rule here. So I'm going to do this one in detail. So first, you want 1 over 2 root 41 minus x squared minus y squared. That's from differentiating the outside. You've also got to differentiate the inside, which in this case is just negative 2x. So this comes out to be x over. Oh, hold on a second. Whoops. Sorry, guys. There's a 4 down there. Minus 4x squared minus y squared. So then if you differentiate that, you're minus 8x. And then that's minus 4x over root. Well, actually, just so you know, this is kind of a clever way to do this. Over f of x, y. Right, that denominator down there, root 41 minus 4x squared minus y squared, that is f. And then the derivative in the y direction, I'm going to skip the uninteresting stuff. It's just negative y over f of x, y, for basically the same reason. If we evaluate f sub x at 2, 3, we already know that the function comes out to be 4. So we get negative 8 over 4 equals -2. And then we plug in 3 for y right here, and we get -3 over 4. I'm almost done with the first part. So z equals the starting value for, I want a slope of -2 in the x direction as x deviates from the point 2. I want a slope of -3/4 in the y direction as y deviates from the point 3. And that there is our tangent plane. So f at 2.1, 2.9, right? It's not equal to the tangent plane. It doesn't exactly coincide with the tangent plane, but it's close. We'll use a little approximation symbol there. And we want 4 minus 2 times 0.1. That's for the 2.1. Minus 3/4 times -0.1 because it went down by 0.1. And this is the same as 4 minus 0.2 plus 0.34, 0.75, 0.75. Minus 1.125, so 3.875, 3.875 minus 0.125. Yeah, it looks good to me. Okay, so just so we're clear, this is an example where we are approximating the value of a function using a tangent plane. What did we do? We found the tangent plane at the starting point, 2 comma 3. That's up to this point right here. And then we approximated the value of the function at the point we care about, 2.1 comma 2.9, by plugging those coordinates into the expression for the tangent plane. So I'm going to just do a definition now. It's just another way of saying the exact same thing. Uh, instead of z, if you write L of xy equals the value of f at the starting point plus, so this is exactly what we've been working with so far today, the slope at that point times how much you change in the x direction, sorry, the slope in the x direction times how much you change in the x direction plus the slope in the y direction times how much you change in the y direction. That's what we've been dealing with the whole time. But if you call it L, that's just common notation. This is another way of saying the same thing. This is the quote unquote linear approximation. So it's the same thing as the tangent plane, excuse me. But if you hear somebody say linear approximation, it just means they found the tangent plane, but they're thinking of it as something they're going to use, linear approximation, to f at this point. They're going to use it for approximating things. So mathematically, it's no different, but sometimes the vocabulary tells you what it is that people are intending to do with the thing they're making. Oh yeah, ba ba doom ba da ba ba. Okay, that's that part. And then what matters next? Continuity of first partials. Yeah, so differentiability. So again, we don't really define things too rigorously. I think I've said this a few times already. Um, uh, we don't define things too rigorously in these introductory courses, but I'm going to put this way. And this definition is good. It's also conceptually, it's the definition that you would have seen for single variable as well. A function f of xy is differentiable. So this is kind of vague what I'm going to write, but not really. If and only if its tangent plane, or sorry, it's a function of y is differentiable at a point. So let's say at whatever point we're starting at, x initial, y initial. A function is differentiable at that point if and only if its tangent plane at that point. So here's the only place where I'm being vague is a quote good approximation to f. So you think back to when is something not a good approximation in one variable calculus? Well, there's a function with a corner. You know it's not differentiable at that corner. That the tangent plane that I just drew right there, tangent line, because we're in one variable there, is not a good approximation, right? It doesn't get close enough fast enough. Whereas if instead you had drawn something with a curve to it, then you can kind of imagine this is maybe hard to imagine, maybe not hard to imagine, but it becomes a much better approximation up close than it was if you had that corner there. So I'm not going into the precise definitions using words like or letters like epsilon and delta and limit, but there's a way of formally stating this one with the corner is not good enough, and then this one that's smooth here is good enough. When you define differentiability for a function of one variable, the tangent line being a good approximation, so this is good here, and this is bad. That's what it means for a function to be differentiable. And then it's the same thing in higher dimensions. The tangent plane has to be a good approximation, i.e., the graph does not have some kind of surface-like corner, like a mountain peak of some sort. It's smooth there in some sense. The plane really kisses it just right. There's a nice tangent plane there. So that's the idea. And then there's another one of these big old theorems. Um, I guess I'll call it a theorem, but really just, but this is what you care about for this class. If the functions f sub x and f sub y exist and are continuous, let's say everywhere, everywhere, then f is differentiable, differentiable everywhere. I'm going to try to draw one more picture in case anybody's sitting here thinking, like, what does that even say? There is an issue that can happen, and it is not an issue that this course focuses on. It is a pathological issue that is arises from very badly behaved functions that we don't really deal with when we don't have to. I'm going to state it as follows. Let's imagine that the derivative in the x direction of a function is 0 and the derivative in the y direction is 0. Then you would guess that the tangent plane has to be flat. For a badly behaved function, you can create this. I'm going to draw kind of like rippling behavior. So this is like a going around the outside. This is kind of like a ribbon or a napkin or something that's really wrinkled. Actually, I'm drawing it too well behaved. I want it to really fold up and fold down and fold up and fold down. It's possible to do this in a way that the folds are such that uh, I didn't really draw this great actually. Sorry. Let's try one more time. Those blue lines should be straight, but they should be going to the origin. So like this, this, but also this, 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 etc. So you can kind of maybe believe me from this picture that you can get tangent lines in all these different directions that go in all kinds of wonky ways. And there is, I'm just going to say this, there is no tangent plane. But if that happens, if you were ever to be able to design a function like this, which you can do, it's possible, these functions would not be continuous. F sub x and F sub y would have to be poorly behaved near the origin to allow this to happen. I can't believe this happened again. Hold on, guys. Not really sure about this. Let me pull it out a second. Okay. Super embarrassing. Whatever. Um, so okay, yeah, there's a lot of these things we say in these calculus classes where it's like, hey, you've got to be aware of this, but also don't worry, we've designed this course to, or not even designed this course. These definitions of these things are designed, words like continuous, to keep things well behaved because nobody wants to deal with things like this. We don't want to see things like this. So it is very convenient to know that if you have a function f, right? So let's say you start with some function f and you generate its derivatives by some, doing a little bit of calculus, and you find out that this is continuous and this is continuous. Just seeing that those two functions come out to be continuous, which is not that hard to check, then you can know this is differentiable everywhere. It's differentiable at every point. So you can imagine it's nice to be able to say confidently, this does not happen. This weird folding napkin behavior or some other kind of bad behavior does not happen when these two functions are continuous. Okay? So we'll do one. I think there's one example that's going to show you what I'm getting at here. Um, no, they don't have one. Let me just go back to one of my earlier examples and just say something. Let's go to uh let's go to the first one. It's the easiest one. Where was that? Right here. Let's just say, so here's this function f, and you were asked, is this function differentiable? You can just check. You take the first derivative, you get this. This is a linear function that's continuous. The first derivative in y is also a linear function. It's also continuous. So that's a continuous function. That's a continuous function. Definitely, that's differentiable. That's the idea. You simply check the continuity of the first derivatives, and then you can deduce the original function is differentiable. So I don't have an example ready to go on that, but keep that in mind. There's one more idea to get through for this section, and it's the idea of a differential. And this is not very different from tangent plane or linear approximation. There is a small, subtle difference. One more time, let's recall one variable calculus. If this is x and this is f of x, and you have some function and some starting point, then when you build a tangent line, you often see it done this way. There's an amount that you change in x and a corresponding amount that you change in y. And delta y over delta x is roughly the derivative of f. Now let's do it again. Let's take delta x to be smaller. So maybe that's delta x, and maybe that's delta y. Then if you did delta y over delta x, this is not going to come out to be the same as the guy above you. In general, it might if you're lucky, if it's a straight line or whatever. But either way, that should also be, and in general, it's a better approximation as you get smaller and smaller for the derivative f prime at the starting point x. So this idea of this delta x and this delta y, there's an amount that x changes and a corresponding amount that y changes. There's something that happens. Well, okay, so here's what they do. They'll write something like this. dy equals f prime of x dx. Hopefully you guys have seen something like that before. That right there is the tangent line. So let's go ahead and draw that in. Well, hold on. Here we go. This is the subtlety here. Imagine we're starting right here. So this is, that right there is x. If you zoom in there, you go over by an amount dx, and there's a straight line here. And the straight line goes up by an amount dy, which has to be exactly equal to f prime of x dx. And that straight line there looks a lot like, here we go. If you, if you zoom in here, come on. So I want to zoom in there. Whoops, come on, come on, come on. And you try to trace the actual function. So the actual function is not a straight line, but it's very close to a straight line. So maybe it's like this. And so this over here, they're going to call this delta x, and the amount it goes up, delta y. Delta y is how much the curve actually went up. Delta x is how much you went over. Down here now, dx, still how much you went over, but dy is how much the straight line changed. So what the whole reason for all this notation is just to keep the ideas of how much the actual function changed and how much the linear approximation changed separate from one another. The end result or the upshoot would be that dy. So let me remind myself how they like to write this. Well, basically this. They basically write this. dy is roughly equal to delta y. So the change in the function and the change in the linear approximation. Linear approximation. So if you know the linear approximation, you can also easily figure out the change in the linear approximation. This is why I say it's almost the exact same idea. But strictly speaking, the linear approximation goes through the point that we started with. Let me do one more color. The linear approximation goes through the graph itself, but the change, it's down there. Okay, whatever. So that's all formulated for one dimension. Let me just write out very quickly because I think I'm pushing the limit of my time. Formalize those ideas for 2D, and then maybe I can stop there. So yeah, so let's get a quick picture in there. Given a starting point, we can go over by an amount delta let me use a different color. We can go over by an amount delta x. We can also go over an amount in the other direction, delta y. And this will give rise to a change in z, a delta z. So let's say this gives us this new point here, right? We're over there now. And then the function, maybe the function started off at this value, but as we went from here to here, the function went up, maybe, to some other value. So the let me use red. The change, the amount that function went up there is equal to the value, the value of the function at the new point minus the value of the function at the starting point. So that's the actual change in the function. And if you simply design not the tangent plane, it's not quite the tangent plane, but dz equals to, so just the derivatives now, the change in the tangent plane, sorry, I don't need the initials there. In the x direction, and then also the change in the tangent plane in the y direction, where we're using, I wrote this in the 1D example, delta x equals dx and delta y equals dy. Then this implies dz is roughly equal to delta z if f is differentiable. There is only one difference in all that last thing that I defined, the differential. We did not include the value of the function, right? I didn't put plus the value of the function. So we're finding a parallel plane to the tangent plane. Or let me just go back and think of the ideas we saw today. So here's like a bubble of ideas. We saw the tangent plane, we called it Z. We also called it L of X initial, Y initial. And then the last thing we're seeing is this other guy, this DZ. And these guys are parallel planes. Parallel planes. The linear approximation goes through the function's graph, and it's meant to approximate the function at other places. The differential does not include the value of the function and is meant not to approximate the value of the function elsewhere, but to approximate how much the function changed, delta z. Right? Delta z, look, it's the difference in the function at 2 points. Delta z is how much the function changed. Dz is for approximating the change. So I'm just going to spell this out in quotes as two different kinds of questions. What is f at some new point? Let's say, some point roughly equal to. And then another one is, whoops, come on. How much did f change? Did f change? So what is the value of the function at the new point is one kind of question. For that, you would use a linear approximation. How much did it change? You would use dz. That's the only difference. There's these two kinds of questions. Okie dokie do. Give me 1 second to just collect all this and think this through. Yeah. Okay. So I think all in all, that's pretty good. So that is section 4.4. Email me if you have any questions, and there will be one more lecture for this week covering 4.5, and then I'll finalize the homework for the week, which will be due next Monday. Thank you guys again, and look forward to speaking to you.